We are now going to talk about induced fields. So up till now in this chapter, we've been talking about induced current and we've been talking about EMF. Now we're going to be talking about induced fields. So it's the same phenomena, but we're talking about it in a different way. So we're going to initially think about this by removing the wire, right? Notice that we've been talking about a wire that we're inducing a current in or an EMF around. And so if we have a region of increasing B, we know that we would get an induced magnetic field that needs to oppose it, right? So if I just draw some dots, that represents my induced B. And so you have to have a current in your induced current that would create that. So that's again Lenz's law. And we get a current that creates that. We know that there's an EMF that is creating that current. But what if I removed the wire? And now this is where you have to think about this a little bit, that something is happening in space, right? That when we talked about charges moving, charges experiencing forces, we said that there's this field, and when you put a charge in it, it interacts and experiences a force. But the field is everywhere, whether or not the charge is there. So the idea being that we can say, hey, what would cause this current is in fact an electric field pointing tangentially at the circle, right? That is basically a circular electric field. Now, that electric field should be independent of the charges it's acting on. And the charges it's acting on are the charge carriers in the wire. So if I take away the wire, I am still left with an electric field going in circles. And the idea being that you could imagine placing different radii rings, and you keep getting the same sort of phenomena. And you would have to use Faraday's law to get the exact magnitude of the current, but you would always be getting a current going in kind of the same way in a circle. So the takeaway here is that when you have a changing magnetic field, you induce an electric field in that region of space. Again, in this picture, over here on the right, we only have fields, right? Now, obviously, there has to be some cause of the magnetic field. Something is causing it, something is causing the magnetic field to change. But you can have a region of space without any charges in it, without any currents in it, only with a changing magnetic field, and boom, you get an electric field. So this is kind of crazy and really important. So the first thing, and the book stresses this, and I want to stress this as well, when we introduced electric fields a couple of chapters ago, what probably feels like a lifetime ago for you, we said that, well, it's, a tool we can use, it helps us visualize things, and now we are saying that a changing magnetic field is creating an electric field, and we can then do experiments to see that this is true. So fields are not just ideas. They are not just cute little visualization tools. The field itself is a real thing because we can start seeing the effect of fields that we really can't explain any other way. So that's what's going on here. We would say that we have a changing magnetic field induces an electric field, and you can have nothing else, like that will happen even if you have nothing else in the region. So let's try to understand some consequences of that. So now we have two causes of electric fields, and we need to understand the difference between them, kind of compare and contrast. For simplicity, we're going to call them the Coulomb electric field and the non-Coulomb electric field. So clearly, two different types. We should be able to put all electric fields in one or the other. So the Coulomb electric field, that word should remind you of charges. So the Coulomb electric field is what we originally learned, right? Back first chapter we covered. And so charges, right? These charges cause it. And we know that our lines, if we want to talk about field lines, they start and end on charges. So that's again what we did many chapters ago. The new thing that we have is a non-Coulomb electric field, and in that case you have changing magnetic fields that cause these electric fields. In this case, your lines are going to be loops. And I'll show you a picture of that. But you don't actually have your lines end and begin on charges. This is now independent of charge. So be careful about that because the pictures are going to look different, and some of the rules we learned about drawing electric field lines at the beginning won't be true anymore. Again, you can have loops of electric field lines which couldn't happen when they depended upon charges. Okay, let's talk through a calculation of induced electric field. Now the good news is that there are very few geometries that we can talk about the induced electric field for. So the derivation or the calculation I'm about to show you is really the only one you're going to do. It's really hard to construct other scenarios that are doable at the level of math sophistication that we use in this class. So notice that we have a solenoid. So you have your current that comes through a loop, and that creates more or less a uniform magnetic field. Now obviously this picture isn't the best solenoid, but you get the idea. So then we are looking at these magnetic field lines. We are not showing the solenoid right now for simplicity, but the solenoid is what's creating that uniform magnetic field. The induced electric fields are going to be these ring shapes that go around the magnetic field. Whether they go clockwise or counterclockwise depends on to whether your magnetic field is increasing or decreasing. And you can think through this. There was an example in the previous video where we put down a little ring inside our solenoid, and we saw that when your current increased or decreased, you got induced currents in that ring. So effectively, we're saying, hey, there could be a ring here or not, and so we're just thinking about what the electric field would look like even if the ring wasn't there. So hopefully that makes sense so far. Again, you just kind of need to know that the electric fields are going to form circles, right? If your magnetic field is in these straight lines, and is increasing or decreasing, you induce circular electric fields. And these are again going to be those non-Coulomb fields. So the calculation that you use is this crazy surface integral. So this thing means it's a line integral, not a surface integral. So you need to integrate on a curve, and you want to simplify this as much as possible. So ideally, we want our E.ds to become a multiplication problem. And in this case, we can do it by basically saying, hey, my electric field is always going to be tangent, so this is actually going to simplify, especially if I choose circles where I expect my electric field to have the same magnitude. So again, you can use a symmetry argument to simplify this down. So the integral of your induced electric field, right? So this is your induced E that you're calculating, is then going to relate to the area and the magnetic field. This is again a simplified form. You should notice that this looks a little bit like Faraday's law, but we're really going to restrict how we think about this to this sort of a case. So we say that B dt is going to be this change that induces this electric field. And area in this case is going to be the area inside your integration curve, right? So we have a curve, we have the area inside of it. So when we had Faraday's law, we usually had a wire to explicitly think about. Now we don't have a wire, right? We're not just talking about the area inside the solenoid, we're talking about the area inside our integration curve. This integration curve is kind of like a Gaussian surface. It's not a physical object, it's just the mathematical path in this case that we're integrating over or thinking about the flux inside. So the way that I'm going to simplify this is again just saying, hey, the circumference of my circle is 2 pi r. E is always tangent, so that dot product is very simple. And so this is just going to be a constant electric field that always points in the direction of my little ds here. So that just becomes the circumference of my circle, right? That's what 2 pi r is, multiplied by the electric field, which is uniform over that circle. Well, that leaves a dB dt on the right. So area is just going to be 2 pi r. Again, r in this case is the r of the path I just integrated around. So when I solve for E, the whole point here was to actually calculate the induced E. I divide by 2 pi r on both sides, so I'm left with r over 2. So this here is the answer. And it's telling you how the strength of the electric field varies. Notice that as your radius increases, your electric field also increases. So as you have many, many circles that are around them, you have a bigger field strength on the outside than you do towards the center, where you assume that this value, again, you're in a uniform electric field that's changing in all the same way. So again, we're not going to see many different calculations. That really is going to be it, but please make sure that this makes sense to you.